Okay, let's start. So one organization issue. I will be given some automatic tests through smart LMS. Unfortunately, due to synchronization problems, I don't see even all officially enrolled participants in smart LMS. So it's important, if you want to follow the course, it's important that I I should give you an access. I can do it by hand, but please send me an email. My email address is written here. Please let me know so that I get you enrolled in the Smart LMS course by hand. Пожалуйста, мне напишите, чтобы я вас внес в этот курс, если у вас нет доступа. Okay. Now, the course is announced in English, and I have to speak English because not all participants understand Russian, but но если вы что-то хотите спросить по-русски, не стесняйтесь, я могу повторять по-русски, и мы можем и так, и так. So if you have any questions, feel free to ask either in English or in Russian. Unfortunately, cannot guarantee that we can process other languages. So this lecture will be informal. I will do some hand waving, and I will show some pictures, but we will go more formally and more systematically over the same material later on. Maybe not over the same material, maybe this informal slides will be somewhat more specific, but still they are rather central to the theory. So let me start with major concepts of one-dimensional complex dynamics. I don't know why it switches. So these are Fatou and Julia sets. What we consider, so on the one hand, maybe it's too loud. So on the one hand, we consider very familiar algebraic objects. These are rational functions of one complex variable. So in terms of, from the viewpoint of algebra, there is nothing simpler. You can write an explicit formula. You can even write as simple formula as z squared plus z squared plus c, z squared plus a constant, a quadratic polynomial. But the questions you ask about these very classical objects are not the type of questions people ask in algebra. What we will be interested in are questions of dynamics. That is, you want to iterate the function, apply it over and over again. You take a point, z, you take f of z, you take f of z, f of f of z, and so on. This way, you form an orbit of the point. So this is, I'm not sure if you see, right, you should see something on the screen. So this is how an orbit is formed. You iterate the function and you apply an nth iterate to a point z. In this way you get a sequence, and this sequence is called the orbit of z, and the question is what the orbit looks like, how its behavior depends on the choice of the initial point z, and maybe more importantly, how it depends on the choice of f. So if we change z, what happens, and if we start varying f, what happens? Such questions, in principle, if we ask them not about the specific types of dynamical systems, but more general dynamical systems, they are of crucial importance, even in engineering, because if you constructed some dynamical system, say a robot, you want to know how the behavior of this robot, how stable the behavior of this robot is. That is, how much what it does depends on the construction, that is on f, and on the initial state of the orbit, that is on Z. Okay? Now, in our specific case, we deal with points and the map. We can also think of this geometrically. Say we can draw an arrow from each point Z to the corresponding point F of Z. That means drawing many arrows. From every point there will be arrow to the next point. And what we are doing, we are jumping along the arrows and see what happens. Now, the Fatou set can be defined as a set of points whose orbits are stable. That is, they depend continuously on the initial point in a suitable sense. It's enough to take the spherical metric and say that the continuity, the continuous dependencies in the sense of the spherical metric. Later on, we'll discuss a more analytic definition, which uses the concept of normal family in the sense of Montel. But for now, this definition is equivalent. So it's just a set of points whose orbits are stable. That is, if you change the point slightly, then the orbit also varies slightly. Doesn't bifurcate too much. So this is the Fatou set. And the Julia set is the complement of the Fatou set. These are the most important sets. Both sets are invariant in the sense that if you take a point in the Fatou set and apply the map, then you get another point in the Fatou set, and the same for the point in the Julia set. Now, the Fatou set is well understood. You have very well understood and explicitly described dynamics on the Fatou set. This is not at all trivial, but in principle, this question is completely solved. You know everything, well, maybe not you, but in principle, people know everything about dynamics on the Fatou set, but the dynamics on the Julia set is a much more complicated matter. Well, because it's unstable, in more cases one can say, one has to make a rigorous sense of this, but one can say that the dynamics is chaotic on the Julia set. Any questions? Yeah.
I have an organization question about the mark. So, what is the formula for the mark in this course?
Okay. Have you seen the web page for the course? It's written there. It's 50% for the accumulated grade. That is everything you do in the course. Mostly this means automatic tests and smart LMS. So 50% is automatic tests and 50% for the final exam, which will be a take-home exam. You will be given an individual problem, not a too difficult one, but an individual problem, and several days for solving this problem. Other questions?
Правильно ли я понимаю, что множество точек непрерывности у F само в себе не обязательно открыто?
Точек.
Что множество ФД это множество точек в окрестности, которые прописаны непрерывно. А если мы возьмем множество просто точек непрерывности, это что-то другое будет?
Если мы возьмем просто... в смысле, что орбита просто не обязательно в окрестности, а просто в точке зависит непрерывно. Просто в точке зависит непрерывно. Сейчас я... Да, мне кажется, что там будут отдельные контрпримеры, что если вы возьмете... Нет, хотя нет, сразу не могу. Для параболической точки даже в отдельной точке не будет непрерывно. Не знаю, может быть, можно и просто сказать, что непрерывно в точке. Вот. Но если вы скажете, что непрерывно в окрестности, то отсюда сразу очевидно, что оно открыто. А если вы скажете, что просто непрерывно в точке, это еще как бы открытый вопрос, открыто оно или нет. So I'm not sure if it's enough to require the continuity at one single, just at one point. I said that a point belongs to the Fatou set if the orbit depends continuously on the initial point in some neighborhood of this initial point. The question whether it's enough to require that the continuous dependence holds just at this point rather than in the neighborhood. Well, anyway, this is more standard, and it makes more sense to require something of the neighborhood, because this is what maybe it's indeed enough to require that. But anyway, even if it's true that these two definitions are equivalent, it's not so simple to prove, because one needs to consider cases. Okay, so these are pictures of some Julia sets, and so these are Julia sets of rational functions. Not all of these Julia sets can be realized as Julia sets of polynomials, but these are Julia sets of rational functions. So one example is that the Julia set of a rational function may be the whole sphere. Now this picture, it doesn't look uniform because you see some distribution in the sphere. Some points are lighter, some points are darker, and this distribution corresponds to some invariant measure that's invariant under the action of the map. This measure does not have to be uniform, but you get the whole sphere as the Julia set. The Fatou set is empty in this case. So now, another case is you may have a Cantor set. It's possible even for quadratic polynomial, for z squared plus c, where c is a constant. If you choose c properly, then you may have a picture like this. So in which sense this is a Cantor set? A Cantor set is usually defined as a subset of a line. Now, what I mean is a subset, a compact subset of the sphere that is homomorphic to the usual Cantor set. And this happens rather often because what you need to have is that you need to have a compact set that doesn't have any isolated points, and such that it's totally disconnected in the sense that every connected component is a point. So all components are points, no isolated points, and a compact set, more than one point. Well, more than one point is automatic because you don't have isolated points. So then it will be automatically homomorphic to a Cantor set. So this happens rather often. Also, you may have Sierpinski-Karpitz Julia set and Cantor union of ovals, Cantor union of circles, something homomorphic to circles. Jordan curves are, well, by definition, something homomorphic to circles. You may have all this. Questions? Okay. Now let me consider a specific, a special case, namely that of polynomials. Now, polynomials are, of course, special from the algebraic viewpoint, but they're also special from the dynamical viewpoint. What is dynamically so special about polynomials is that every polynomial has a point with very special properties, namely the point at infinity is the point whose full preimage is just this point. Now this happens very rarely, and for polynomial, for every polynomial you have such a point, and this will be unique unless you have z to something, z to the n. For z to the n you have two such points, and for all other polynomials you have only one such point. So the full preimage of this point is the point itself. Okay? Now you can always change coordinates so that to make a polynomial monic, that is to make the highest coefficient equal 1. So it starts with z to the n plus something plus lower order terms. And given a monic polynomial, complex polynomial, you can define the field Julia set as the set of all points whose orbits do not escape to infinity. Now, it's the same as to say that the orbits are bounded, because if a point escaped far enough, there is no way it can go back. Because if the modulus of z is very large, then the highest order term dominates. So z to the n appears much bigger than all other terms, and it forces the point escape further to infinity. If a point starts escaping, it cannot, there is no way of going back, it will escape to infinity all the way. So you have this field, the so-called field Julia set, and it happens, and this is a special property of polynomials, this formula, that the Julia set is the boundary. So this is a much simpler description. The Julia set is the boundary of the set of all points that do not escape to infinity. Equivalently, it's the boundary of the set of all points that do escape to infinity. It's the common boundary between the two sets. And again, this is only true for polynomials, not for all rational functions. And the Fatou set is the complement. So the Fatou set always contains the so-called Bayesian of infinity, the set of points that escape to infinity, but there may be other components. For example, in this picture, this is the so-called basilica. And you see many components. Some of them are colored blue, some of them are colored green. And all these components are Fatou components. The Julia set is just the boundary of the figure. Now, a quadratic polynomial is just any polynomial of degree 2, and by changing variables, you can always make this quadratic polynomial look like z squared plus c. So z squared plus c is not some funny choice. It's just that any quadratic polynomial can be reduced to this form by an affine conjugacy. And there are some open equations even for this family of polynomials that look very simple from, well, if you do algebra, but if you do dynamics, they show complicated behavior. One of the famous sets in complex dynamics is the so-called Mandelbrot set. It consists of all parameter values C such that the corresponding field Julia set is connected. So here I need to pause and let you digest this, because one important thing is that points of the Mandelbrot set are parameter values. That is, if you choose a different point in the Mandelbrot set, that means that you change your dynamical system. Каждая точка множества Мандельброта соответствует своей динамической системе. If you take different C, then you get different dynamics, different z squared plus c. So the Mandelbrot set itself is a kind of table of content. Yes. Связаны, да. Множество таких значений параметра, для которых заполненное множество Жуля связано. So the importance of this set is that it gives you a table of contents for the entire family of maps z squared plus c. If you pick a point in the Mandelbrot set or outside the Mandelbrot set, depending on where this point lies, how it is located relative to other important parts of the Mandelbrot set, you can tell a lot, or let's say an expert will be able to tell a lot about what happens to the dynamic of the corresponding parameter, z squared plus c. Now, if you just given a specific value of c, in general, you cannot tell much because I say C is equal to minus 1.5. I cannot say much about this, about what the dynamics of Z squared plus C looks like. But if you show me this value in the Mandelbrot set, I will be able to say more. For example, if a point is outside of the Mandelbrot set, then the field-Julia set is the Cantor set. And if it's inside, then it's connected by definition, but in general, you can say more depending on where exactly in the Mandelbrot set you're located. So the theorem is that, well, this is what I said. A point lies out, not quite what I said. You can decide whether the parameter value lies in the Mandelbrot set or outside by looking at just one specific orbit. Namely, it's enough to look at the orbit of the critical point 0. 0 is the only critical point of Z squared plus C in the finite part of the plane. The critical point is where the derivative vanishes, but it can be defined dynamically. A critical point is formed by 2 points. So if you take the image of the critical point, the so-called critical value, then the only pre-image of this image is the critical point itself. If you take any other point, then there will be 2 pre-images. I'm talking about quadratic polynomials. For quadratic polynomials, the critical point is where you have only one, is where the 2 pre-images merge together. Now, if you look at the Mandelbrot set and zoom in, you will see many other copies of the Mandelbrot set. And in fact, so this is what you can see in the figure right now. But more than that, the Mandelbrot set is universal in the sense that if you look at some other parameter plane, not just parameter plane of Z squared plus C, imagine some parameter plane, a family of polynomials, or not even polynomials, some analytic functions that depend on just one parameter C analytically. If you have such a family, then almost surely in the dynamical plane of C, you will see copies of the Mandelbrot set. So in general position, you will see copies of the Mandelbrot set. Exceptions are when the dynamics are trivial, there is no dependence on C at all, then you will see nothing in the dynamical, in the parameter plane of C. Or maybe there are consistent, say, there may be consistently multiple critical points. Then you will see something very similar to the Mandelbrot set. Okay, so here are 2 examples of quadratic Julia sets. And the first example is probably the simplest example that we can discuss right now and in full detail. If you take Z squared, just Z squared, C is equal to 0, and look at the dynamics of this map, it can be completely understood. Namely, take any point inside the unit circle, point Z with modulus Z less than 1. If the modulus of Z is less than 1, then what happens with the orbit of Z? Можно по-русски отвечать. Стремится к нулю. It goes to 0. Moreover, it goes to 0 super exponentially fast. It would go to 0 exponentially fast if each time you, say, multiply it by 1/2, but you square it at each time. So you multiply by a number which itself becomes smaller and smaller. So it goes to 0 super exponentially fast. And so all orbits that happen inside the unit circle go to 0 super exponentially fast. All orbits that originate outside the unit circle, they escape to infinity super exponentially fast. Okay? And now the only interesting thing happens with points exactly on the unit circle, and these points stay on the unit circle. And the dynamics is rather basic and simple. Still, it's in some sense chaotic, because what happens on the unit circle is a so-called angle doubling map. Each time you double the angle. If every time you double the angle, then this behavior is very sensitive to the initial point. If you make even a very small mistake in the choice of the initial point, then after a while, the mistake accumulates, it doubles on each step, so that after several steps, you will not know where your orbit will lie. Okay, now this is the simplest example. There are two components of the Fatou set. The blue component consists of points that go to 0, and the red component consists of points that go to infinity. Now, if you change the parameters slightly, then you don't have a drastic change, at least in terms of topological dynamics. What happens with red points, basically nothing special happens. Red points are still attracted by infinity, and they go there super exponentially fast. Nothing changes. Now, inside the figure, so the figure is not a unit circle anymore. If you look closely, you will find out that this is a Jordan curve, in the sense that the boundary of the figure is still homomorphic to the unit circle. However, if you compute its dimension, it will be strictly bigger than 1. And the figure is fractal. It's almost no way differentiable. So it becomes subtle if you look at from the viewpoint of metric geometry. But from topology, it's just a circle. So topologists will say that it's just a circle, nothing more. And what happens inside this circle is still very basic. You will have some attracting point, not super attracting anymore. 0 will not be a fixed point, but there will be some fixed point nearby. And all blue points will be attracted to this fixed point. Now, you see something, some non-uniform distribution. You see some light spots all around, right? What light and dark means? The lighter points are points whose orbit get faster to a small neighborhood of the attracting fixed point. Why do we see many light spots? Because, well, you have one fixed point, you have a preimage of this point that gets right to the fixed point in one step. And so all points nearby will go very fast to this point, right? And you have 2 preimages of this preimage, you have 4 preimages of this 2 preimages, and so on. So around each of these iterated preimages, you will see some light spot. Okay? Mm-hmm.
Там разве не две должны быть особые точки?
Что значит особая точка?
Критическая. Вы говорили, что здесь 0 не критическая, но другая критическая.
Нет, 0 критическая. Я сказал, что 0 не является неподвижной точкой. 0 по-прежнему критическая, производная в нуле равна нулю, но она больше не неподвижна. А неподвижная точка – это решение уравнения z в квадрате минус 0,2 равняется z. A fixed point is a point is the solution of the quadratic equation. Z squared minus 0.2 is equal to z. There are 2 solutions of this equation. One solution is inside, another solution is on the circle.
То есть между особыми точками и множествами Жиля связи не упоминалось.
Между какими особыми? Между критическими точками и множеством Жиля? Пока не упоминалось. Так, хорошо тут? Да? Okay. This is what happens if your parameter goes to the value of minus 0.75, that is minus 3/4, from inside of the main component of the Mandelbrot set. Now I don't have a figure for the Mandelbrot set, so here is the figure of the Mandelbrot set, and you will see So here I can, never mind. So this is the so-called main cardioid, and what happens is that the parameter value goes to here. Do you see the pointer? Goes to here from within the main cardioid. And what happens is some kind of bifurcation, because until we reach this point, what we see is just a topological disk. So inside this disk, all points converge exponentially fast to some fixed point. Outside, all red points escape super exponentially fast to infinity. And on the boundary is still a topological circle. And the topological dynamics on this boundary is still conjugate to the angle doubling map. That means that you can introduce a parameter on this circle so that this parameter gets doubled every time you apply the map. Okay? But at this value of the parameter, at -3/4, what happens is that the topology of the Julia set changes all of a sudden. So before, what you had before was a circle, and now at the point of bifurcation, what you have is not a circle. Is the circle pinched at countably many points, countably many places. Это все еще топологическая окружность. Там еще не пережалось, а потом одновременно пережимается в счетном числе мест.
Ровно в 4
Mm-hmm. And you can see this bifurcation if you look at the Mandelbrot set, because in the Mandelbrot set you pass from one component to another. So let me give another example. So what happens with z squared minus 1? It's more complicated than just z squared, but it's a kind of rather simple and interesting, because the special thing about this polynomial z squared minus 1 is that the critical point 0 has period 2. It gets mapped to -1, and -1 is mapped back to 0. Okay? So the critical point 0 lies in the periodic 2 cycle, 0, -1. Now, all points that are nearby, near 0, they also get close to -1 and close to 0 and close to -1 and so on, and they converge super exponentially fast to this super attracting orbit. But now the super attracting orbit is of period 2. I colored all points that converge to this cycle in green and blue, so that all green points are mapped to blue points, and all blue points are mapped to green points. And this can be done consistently. Now, what you can also do in this picture is you can draw an invariant line segment like this, from -1 to 0. It's invariant in the sense that if you apply the map, it's mapped to itself. And it captures a lot of dynamical features of this map. You can also model this. Map by the so-called invariant lamination. How you draw this is as follows. So what I show in the figure are half circles, but you can draw chords. It doesn't matter. So what I draw are geodesics in the sense of the Poincare metric in the unit disk, but you can also draw geodesic in the Klein metric. The only difference is that this will look worse. I mean, the Poincare geodesics look better because they're more visible. Now, the only important thing is that which points are connected by these geodesics. And the first thing you connect is the point with the argument 1/3 here, Do you see here? So 1/3 is 1/3 of the whole circle. So you measure, you introduce the coordinate on the circle so that the full circle is 1 rather than 2 pi. Okay, and this is 1/3, and you connect it, this is 1/3, and you connect it with 2/3, because 1/3 is mapped to 2/3 under the angle Dublin map, and the other way around. And if you connect these 2 points, then you get a fixed point, a point that gets mapped to itself. And now you pinch the unit circle along this chord. So you collapse this chord, and then you will have 2 components. Now you also need, if you collapse at one place, you also need to collapse at countably many places. Namely, you need to take care of all the iterated preimages. And so the entire picture of the lamination is formed by iterated preimages of this single chord, 1/3, 2/3. But if you specify a way of taking these iterated preimages, then you get this lamination. A similar construction is possible for the so-called Duadi rabbit. It's the name goes back to Adrien Duadi, one of the founders of this science. And why it's called the rabbit, well, it may be difficult to explain. There is some similarity with the rabbit. The similar thing is that you may imagine that some part of this figure is a body of the rabbit, and some part of this figure represents a pair of ears. Okay? But this is the end of the similarity, because otherwise it's a fractal rabbit, because you will have infinitely many points on the boundary of the body at which pairs of ears grow, and the same thing on the boundary of each ear, and so on. You can also draw an invariant graph. These are not straight line segments. If you want to make it strictly invariant, then this will be some curves. But there is an invariant graph like that. It's called the Hubbard tree. And you can also draw a lamination. The difference with the basilical lamination is that you'll have not only chords, but you'll have some triangles formed by chords here. So you see this triangle, it has vertices at points 1/7, 2/7, and 4/7. And 4/7 is mapped to where by the angle Dublin map? Yes, it gets back to 1/7. So the triangle itself is invariant under the angle Dublin map, and if you collapse this triangle, you'll already see this basic shape with the body and a couple of ears, but you will have to collapse it infinitely many places to take care of all the preimages. Okay? Да. Еще раз, существует ли что?
Существует ли отображение самого диска такое, что если мы возьмем дугу и будем прообразы ее брать в этом отображении кратно, то получится все вполне дуги сразу. То есть работает ли это не только с концами, но и со всеми?
Еще раз повторите, существует ли...
Существует ли отображение неокружности, которое...
Да.
У нас есть отображение окружности z в квадрате.
Да.
Такое, что мы возьмем концы одной дуги, берем прообразы и получается концы всех.
Да.
А существует ли отображение диска, такое, что мы берем дугу, берем прообразы всей дуги,
Угу.
и это будут все дуги.
Да, существует, конечно.
Z в квадрате то же самое.
Нет, это не z в квадрате. The question was whether you can extend the map z goes to z squared. The map z goes to z squared is defined in the unit circle. The question is whether you can extend it inside the unit disk so that the lamination is invariant under this extended map in the well, in the usual sense, that you apply this map not only to the endpoints of the chords, but to the chords themselves. Yes, you can construct this map, because first of all, by mapping the endpoints, you know which chords are mapped to which chords, right? So this is first thing that you need to know. Now, if you know that one chord should be mapped to another chord, you can map it linearly. You mean you extend it as an affine map to the chord. Now you define the map on all the chords, and it suffices to extend it inside each complementary component. Now the boundary of each complementary component already knows where it maps and how it maps, right? And the issue is only extending it inside. You can choose a center of each component and extend it radially.
Правда, что внутрь образа области не попадают никакие еще дуги. То есть, если мы про образы будем брать,
Правда. Вы можете так устроить, что каждая компонента отображается в другую компоненту, как разветвленное накрытие, ветвящееся только в центре. И тогда прообразом границы будет только граница. Это сделать очень просто. Упражнение как-то сделать. Так, хорошо. Now, another picture is the so-called airplane. Now, what happens with the rabbit, I forgot to say this, and with the airplane also, is that you have a periodic cycle of period 3 containing the critical point 0. So for the basilica, the critical point had period 2, and now for the rabbit and for the airplane, it has period 3. So the airplane looks, the picture is not very, you don't see much in the picture, because many fine details are just too small to be seen. But basically what happens is that you see some straight line interval. Well, it's not at all important that it's straight line, but it's something homomorphic to a straight line. You'll see an interval. Then you removed countably many open subintervals from the interval, so what remains is a Cantor set. But in each hole of the Cantor set, you put a disk. Okay? So instead of a hole, you put a disk. This is called a Cantor necklace, because you put a gem in each hole. And you will see, so first of all, you will see this Cantor necklace. And then if you take any disk, then there will be countably many Cantor necklaces grown out of the boundary of this disk. So you will see many other disks, right? And so on. So this is the picture you will see, and the corresponding lamination is what you see here. The difference with all other laminations you have seen is that for the basilica and for the rabbit, the laminations consisted of countably many leaves, that is, countably many chords. Now you'll have uncountably many chords by doing not only pre-images, not only pullbacks, but also the limits of pullbacks. You will also need to add the limiting leaves of this lamination. So this is a picture for a dendrite. A dendrite is something that doesn't have, so a picture is like that. It looks like an infinite graph. So the difference with the usual graph is that you have infinitely many vertices. Basically, a set of vertices is dense in the dendrite. Vertices means points that separate the set into more than two components. But there is no interior. So the entire Julia set is just this dendrite, nothing inside. And the corresponding lamination is what you see here. Are there any questions?
Правда, что период 2, дугой соединенной точки с периодом 2.
Вот в этой, в дендрите, что?
Какие точки здесь соединяются дугой?
Дугой? Да. Угу. То есть как вообще составить вот эту ламинацию? Вы про это спрашиваете, да? Угу. Да, сейчас скажу. So an important thing is that what you
Я понял. Существует отображение из окружности границы нашего множества, то есть вы самой...
well, this is not an explicit description, but in principle, yes. What you see here in the picture, so what you see here are infinitely many triangles and infinitely many chords. Now what you do, you collapse every triangle to a point, and you collapse every chord to a point. So you have a disk, and you define some equivalence relation on the disk by identifying all points in the same triangle and by identifying all points in the same chord. So the quotient space of the disk with respect to this equivalence relation is homeomorphic to the dendrite. This is a precise statement. But this doesn't give you a recipe for constructing this lamination. So a more precise recipe for constructing is that you need to, first of all, you need to draw some diameter of the disk. And this diameter will represent a critical point that happens to be in the dendrite. In spite of other cases we considered, the critical point 0 lies right there in the dendrite. And 0 is mapped to I is mapped to minus 1 plus I, and minus 1 plus I is mapped to where? Say it again. It's mapped to minus I, and minus I is mapped again to minus 1 plus I. So the critical point 0 eventually lands, actually immediately lands, in the 2 cycle, right? The 2 cycle consists of minus I and minus 1 plus I. And you need to model the situation for the lamination, namely you take a point on the unit circle with the same dynamics under the angle Dublin map. The 2 cycle is the cycle 1/3 and 2/3. Now you take a pre-image of 1/3, which is 1/6, right? You take further pre-image, which is 1/12, and draw a diameter whose endpoint is 1/12, 1/12. Now you collapse this diameter, and you collapse all pullbacks of this diameter. So you draw the diameter and you draw all the pullbacks. This is how you draw the lamination. I don't give full details now, because my purpose here is just to show you some pictures, and we will discuss things much more systematically starting the next time. By the way, the main textbook is Milner's book, and I've put a link. In SmartLMS, I gave you a link to a folder containing a copy of this book. I don't make it public because it's not legal, but it's legal to share it within the participants of the course. So, okay. this is a general concept of an invariant lamination. By the way, we will not discuss invariant eliminations because Milner doesn't like invariant eliminations. I don't know why, but somehow this concept goes back to William Thurston. It goes as follows. So if you know that the Julia set of some map is locally connected, then it can be described. So local connectedness is some topological property which you must know, right, from the basic course of topology. Локально связанное множество. Все знают, да? Locally connected sets.
Я знаю определение, с которым его легко спутать. Из-за этого, я не вспомню правильно, не могли бы вы повторить, если это займет достаточно много времени.
A locally connected space is a space, so there are several inequivalent definitions, but if we are talking about compact subsets of the plane, they are all equivalent. So let me put it as follows. So locally connected continuum in the compact connected sets and compact connected set in the plane is the one for which every point has a base of connected neighborhoods. Does it make sense? У каждой точки есть база открытых окрестностей. So if it's locally connected, then you can show, well, it may not be obvious, but just believe me, you can show that it can be represented as the quotient of the unit circle by some equivalence relation. And this equivalence relation is invariant under the Engel-Dublin map in the sense that if you have equivalent points, that the images are also equivalent. And you can also group their pre-images so that they will be equivalent. Classes of this equivalence relations are finite, and their convex hulls are pairwise disjoint polygons or chords inscribed into the circle. This is what we discussed in particular cases. So the corresponding invariant lamination is just the set of all these chords. Just enough to take all the chords, just not even take polygons, just chords. Invariant laminations exist even if the Julia set is not locally connected. And this is a funny story because this creates two parallel worlds. One world is the world of, well, whatever, the world of polynomials, analytic polynomials, that live in the complex plane. And another world is the combinatorial world of invariant laminations. And these worlds sometimes match in the sense that one is topologically conjugate to the other, and sometimes they diverge when the Julia set is not locally connected. Okay, so this is again the Mandelbrot set. Inside you see the component called the main cardioid, and in this main cardioid, somewhere inside, the center of this main cardioid is the point 0, which we discussed, that corresponds to the map Z squared. The dynamics of this map is what we discussed before. Now, if you go like that, if you go from the center of the main cardioid towards the point where the next component is attached, this point will be -3/4, and this is exactly where the bifurcation happens. It happens as you pass from the inside of the main cardioid to the inside of the circle here. By the way, what you see here as a circle is a Ginian circle. This is a circle centered at -1 and of radius 1/4. And this is the only Ginian circle that appears as a boundary of a component of the Mandelbrot set. And the main cardioid is the only Ginian cardioid. Other components may look like circles or like cardioids, but they don't. But they are not actually circles or cardioids. Anyway, in this Ginian circle, in the center, you will see the squared -1, which corresponds to the basilica. Now, the rabbit is here. It's another component attached to the main cardioid. The complex conjugate value is the so-called core rabbit or anti-rabbit. This is just complex conjugate of the rabbit, nothing interesting. And the airplane in somewhere here, it's too small to be seen carefully, but you see some, well, you may see something here, but if you zoom in, you will see a cardioid, something that looks like a main cardioid. And inside this cardioid, the center of this baby cardioid will be the airplane parameter. Ну, там кардиоиды, которые вы на картинке не отличите от настоящей, но на самом деле это один из овалов алгебраической кривой очень высокой степени. Потому что это множество Мандельброта, вот то, что видите, это одна частная кардиоида, одна частная окружность, а все остальное это овалы алгебраических кривых очень высокой степени. Another funny thing, so this is one of the copies of the Mandelbrot set that you see in the Mandelbrot set itself. So this is another instance of self-similarity of the Mandelbrot set. And what you see as the QML here is a lamination, not an invariant lamination, but a lamination that represents the Mandelbrot set. So you can define it very explicitly. There is a very explicit construction that allows you to draw all these chords and polygons. And if you collapse all these chords to points and all these polygons to points, then you get some quotient space, which is hopefully homomorphic to the Mandelbrot set. And this hope comes true if you prove only one minor thing. If you prove that the Mandelbrot set is locally connected. If you prove that the Mandelbrot set is locally connected, then you'll know everything about the Mandelbrot set. Everything. We know a precise model of the Mandelbrot set. All other questions can be answered very efficiently using this model. The only thing you need to prove is that the Mandelbrot set is locally connected. Fields of metal is guaranteed, but unfortunately nobody so far. Okay. The Mandelbrot set is universal in the sense I already described. If you consider some family of analytic maps that depends analytically on the parameter c, so the example is e to the z plus c. This is not a polynomial because you have some exponential here, but it depends nicely on the parameter c. Analytically means holomorphically. You don't have any C conjugate or something. So e to the z plus c. In this parameter plane, you will see copies of the Mandelbrot set. Z to the fourth plus c over z to the fourth is also it's a parameter plane of rational functions. You will also see many copies of the Mandelbrot set there. The top figure is about this family of rational function, and the bottom figure is about the exponential family. Or maybe not. I'm not sure about the bottom figure, but the top figure is about this rational function. For exponential, it should look, well, I'm not sure. Anyway. So there are very few exceptions. The exceptions are when you have trivial parameter spaces or when you have persistent multiple critical points where the critical points do not separate, that keep being multiple. Then you'll see copies of some the so-called multi-Brot sets. These are just generalizations of the Mandelbrot sets. This is a theorem of Macmillan, Curtis-Macmillan. Now, what should I say this? I'm not sure. Let me go to the next slide. So let me say something about the self-similarity of the Mandelbrot set. I already said this, but let me go over it again. So suppose that 0 is periodic for some parameter value c. If you fix a period and impose that 0 is periodic of this period is this is some algebraic equation on C, right? It's in general a high degree algebraic equation, but the important thing is that there are finitely many solutions of this equation, so you'll see finitely many points. And all these points are the so-called centers of some components of the Mandelbrot set. If you start with this center, then points around, so the center corresponds to a polynomial with a super attracting cycle, where all nearby points go to the cycle super exponentially fast. Now, if you move slightly out of the center, then what you see is just an attracting point. Not super attracting, just an attracting point, to which all nearby points converge exponentially fast. But you will see something very similar. The Julia set will be topologically the same. And even in the sense of topological dynamics, it will be the same. So these parameter values are centers of some components of the Mandelbrot set. Now, the boundaries are just circles. So if you take the cycle of the critical point, the super attracting cycle, then there are points attracted to the cycle. And around each point of the cycle, there is a component of this attracting basin. In general, attracting basin will consist of infinitely many components, some periodic components and some non-periodic components. But if you take only the periodic components around the points of the cycle, you will get the so-called immediate attracting basins. These are disjoint Jordan disks. Now, in these disks, what you can do is you can do the so-called tuning. Instead of a disk, you can put some lamination there and collapse all chords and polygons of this lamination. And in this way, you will get another picture. Whether this picture is realized by some complex polynomial is an issue, but it often happens that the picture is realized by a complex polynomial, and it can be shown that tuning defines a copy of the Mandelbrot set. Namely, if you have a center of some component, then you have many polynomials that look as follows. Instead of these disks that go along the cycle, the disk is just the field Julia set of Z squared. Instead of the field Julia set of Z squared, you put some other field Julia set. And you have a freedom of putting many different field Julia sets there, depending on where in the Mandelbrot set you choose a parameter. And in this case, in this way, you create a small copy of the Mandelbrot set, which is called the baby Mandelbrot set. So this is a kind of explicit description of self-similar corpus. Now, another interesting thing happens if you try to. I will show some movies. Very nice movies, but I need to explain something before showing them. I will show the movies, and that will be it. But let me explain something first. So suppose you are given two quadratic polynomials, and you want to cook some rational function out of these two polynomials. Right? So what you can do is the following. You take two copies of the unit disk and put a lamination in each of the copy, one lamination for the first polynomial, another lamination for the second polynomial. Okay? You glue the two copies of the disk along the boundary using the map Z goes to Z conjugate. It's this map that allows you to glue a sphere out of two disks. If you think about it, when you want to form a sphere out of two hemispheres, the identification you use is the complex conjugation rather than the identity map. So this is how you glue the two hemispheres, okay? And then in the sphere, you have two disks and two laminations, and you collapse everything that you need to collapse in each of the lamination. You'll get a quotient of the sphere. This quotient doesn't have to be homeomorphic to the sphere. This is a bad news. And sometimes it doesn't. Sometimes it's not homeomorphic to the sphere. On the other hand, in many cases it is homeomorphic to the sphere. And in many cases it turns out that not only what you get as a quotient space is a sphere, but also what you get not only the space, not only the quotient space, you also get a map on this space, a self-map on this space. So sometimes it happens that not only the quotient space is a sphere, but also the quotient map is topologically conjugate to a rational function. And in this case, people say that you have a mating of two quadratic polynomials. Okay? For example, you may talk about a mating of rabbit and a rabbit, and it's not always, it doesn't always sound decent. You know, when mathematicians discuss shared matings in a bus or in a train, people get a little bit nervous. Anyway, yeah. Топологически сопряжены. Это значит, что есть такой гомеоморфизм, который одну динамику из одной динамики делает другую динамику. То есть есть такая коммутативная диаграмма. Вот у вас сопряжение, это гомеоморфизм. Вот у вас одна динамика, вот у вас другая динамика. Такая коммутативная диаграмма. Это называется топологическое сопряжение. Понятно? Вот. Но мы про это, на самом деле, мы более подробно про это поговорим еще, когда будем. Окей. So another way of understanding matings is that you just take two Phil-Julia sets and glue them together along the boundary. That's it. So now, this is one of the movies. These movies are made by Arnaud Chérita, a very good French mathematician who works in Toulouse. And making these movies is a very much mathematical activity. In order to create these movies, you need to know a lot of Teichmüller theory. So the теория Тихмюллера. Тихмюллер этот был такой немецкий математик, погибший, кажется, под Сталинградом или где-то, когда в 1943 году. So this is a figure of a mating of basilica and a rabbit. You already see a basilica here, a small basilica, and a small rabbit. And in which sense this is a slow mating? You will see a way of gluing the two things. So some of the lines you see here, they connect the corresponding points. The points that are to be glued together. Now, what you will see in the movie is how the basilica and the rabbit become larger and larger and gets glued to each other. So here is the movie. Isn't that funny? Okay, so this was one movie. So here is another. No, this is the same. This is the same one. Okay, let me not stop it, but
Вот преобразование, которое с ним произошло, это не рациональная функция?
рациональная функция — это то, что вы видите в самом конце. В самом конце вы видите картинку для рациональной функции. Все, что вы видите в промежуточной, это не рациональная функция, это именно способ склеить.
То есть то, что в конце, тут мы применили к двум таким множествам
Да.
рациональные функции.
Нет, в конце вы видите базилику, склеенную с кроликом, и это картинка для рациональной функции, в том смысле, что на базилике действует отображение базилики, на кролике действует отображение кролика, а все это вместе — это какая-то рациональная функция. So only everything happens if you talk about rational dynamics, then the dynamics happens on the Riemann sphere. That is the plane of complex numbers plus a point at infinity, and it's essential that the point at infinity doesn't play any special role. This is a sphere which you can rotate, and nothing happens. I mean, if you rotate, then of course you get a different rational function, but it's still a rational function. Infinity is a special point for polynomials, but not for rational functions. And what you see at the very end of this slow mating is a figure of rational only at the very end. So what you see before is not a rational function. It's just, well, one. So here you see just two copies of the rabbit. Right? You see two copies of the rabbit. And after you glued these two copies, you will see a sphere on which a rational function acts. You can write down this rational function explicitly. But it acts so that on each of the two rabbits, its own rabbit map is acting. More precisely, quotient map of this.
Будет итоговое множеством GDA той рациональной функции, которая действует.
Давайте я запущу, во-первых, эту самую... Нет. Будет ли итоговое то, что в конце получится, да?
Будет ли оно множеством GDA той функции, которая действует? Или вообще
Вот что будет здесь множеством жуля? Вот то, что вы видите, там синие компоненты — это компоненты фату, желтые компоненты — это тоже компоненты фату, а все, что на границе — это множество жуля. Вот то, что вы видите, это как бы как картинка на динамической сфере. So in this dynamical sphere, you will see fatu components colored blue and yellow. So every yellow component you see here is a certain fatu component of this map, of a rational function. Every blue component is also a fatu component. But everything on the boundary, or all accumulation points of these fatu components that are not in the fatu components, these are Julia points. Okay? Now, this is also interesting. Now, what happens if we made a rabbit with the airplane? Let me show. No. No, this is not. The caption is wrong because it's a dendrite plus an airplane, not a rabbit. Not a rabbit plus an airplane. Anyway, so you made a dendrite. Here you made a dendrite with the airplane, and what you see as a result it will be so well. Still, this is some rational function. Okay. Let me not. Now this is also interesting. What happens if you mate a dendrite with a dendrite? You may get a sphere. Really, you can. A sphere can be realized as a quotient of an interval, right? You all know about piano curves, but this is a very particular instance of piano-like behavior because you clue. Да, точки. Okay, ну мы это и делаем. Мы склеиваем границу одного множества жуля, мы склеиваем с другим множеством жуля. Это то, что мы делаем. Правильно? Те точки одного и того же множества жуля тоже могут склеиться между собой в результате этого процесса. Да, конечно. So now we glue two dendrites together and here. This is what happens. You glue two dendrites together and you see how they form kind of piano curve. They fill the sphere. Each of the two dendrites fills the sphere. Да. Ну да, да. Внутренности, они как были компонентами фату, так и остаются компонентами фату. А здесь, so if we mate two dendrites, a dendrite doesn't have any interior. Therefore, there are no fatu components inside the dendrites. Therefore, when you glue two dendrites together, you will not have any fatu components. This means that the result will be a rational map whose Julia set is the entire sphere. Is that okay? Еще вопросы? Вот. Если было не все понятно, то ничего страшного, потому что мы со следующего раза будем обсуждать базовые определения. If there is something that you didn't understand, that's no problem, because starting next time, we'll go on very systematically from the basic definitions. And again, the main textbook is the one by Milner, Introduction to Holomorphic Dynamics or something. There is a Russian translation of this book, which is also posted in the same place. If you are more comfortable with reading Russian translation, then you're welcome to do this. The English edition is more recent, and in fact, the Russian translation, it's a funny story, but the Russian translation was actually published before the first English one. Because here in Russia, people were fans of books by Milner. They just didn't have patience to wait until the official print will appear. And they insisted that Milner sent his preliminary version, preliminary notes for translation. So a Russian version appeared before. And now the second edition is available, so this is also posted, and this is more recent one. Maybe some mistakes and misprints are corrected there, but never mind. Both are fine. And we'll most follow this book, so it makes sense if you read first, and then we'll discuss. Please read the beginning, say, two chapters of this book before the next class, but we'll try to discuss them systematically. And also, please don't forget to let me know by email so that I can get you connected to the course in Smart LMS. Okay, thank you. Презентацию я тоже выложу в Smart LMS и видеозапись, которая сейчас я ее... Упс. И видеозапись тоже, если получится, я это все